Hello. I'm just recording this after the recap has actually happened. So the recap happened yesterday, um, and then I was told during and a bit after the recording that there was a lot of mistakes in it. I'll point them out in the video, but what I'm gonna do is I'm gonna let part of the video which I'm happy with play through, and then parts which I'm not happy with I'm gonna re-record, and then splice that together. It was mainly a problem with the flexure part, which is like essentially like the third part of the question, which you'll see towards the end, maybe like half an hour of the original recording. Originally I saw it and then I was like, fuck, I'm too lazy to fix this. But then I was like, oh no, like there's a certain quality in these videos I want to present. Because if I'm being lazy, especially this might be like the last video I record for a while. Like I've got all the concrete recordings done for term 2 and stuff like that. So this will be the last video on signal lectures for an indefinite amount of time. I don't want to set the precedent that if you watch any of my videos, it's going to be unreliable, it's going to be wrong. Yeah, that's not the kind of teacher I'm trying to be. That's not the type of engineer I'm trying to be. So we're going to go back and we're going to fix it and we're going to do it properly. So yeah, see you in a bit. Okay, little rundown of this course. I would say the majority of you guys are actually pretty up to date with the course, just because you're forced to do 2 assignments, right? First one is tension and compression. Second one's flexure. Now that's not covering everything in the flexure topic. It's not covering everything in the tension compression topic, but like the good news about this course is you're not as screwed as, say, if you're doing geotech and like you haven't really been like following along and whatever, just because of the way the course is laid out. You get paid course marks just for keeping up to date a little bit, which is good. But just remember that only covers the first 4 or 5 weeks. There's a bit more at the end, right? But the good news is like the stuff at the very end, week 10, is beam columns. Beam columns, there's a couple of new topics, but they're mostly just backtracking and doing stuff with compression, which you've already seen. It's doing stuff with flexure, which you've already seen. Just kind of combining it all together, seeing it in practice, right? In terms of the best way to prepare for an exam, I found it like I haven't really like found the perfect solution for what I want to present here to you guys, just because it's very different every year. Like if you guys didn't know, like Brian, your lecturer, he only started teaching last year, and his exam style is very different to Hamid and Mark. I think his name's Mark Bradford. Yeah. Like the previous Steels lecturers, like he inherited the course and is from Gusset or something, so they just like do very different styles of exams. So I can't say for sure what's going to be an exam, but it could be anything. That's what I'm trying to tell you. It could be anything. So in terms of what Brian's provided, I've heard that he's provided 2019 and 2020 paper in Moodle just recently, but apparently he pasted the wrong one, so they're the same. So you got one practice paper in Moodle, and it doesn't have solutions and shit like that, right? Now, over COVID, right? COVID was 2020 to 2023, right? Not 2022 or something. He made really hard, sorry, not him. The previous lecturers made really hard exams, right? Which is what I'm going to go through today. So don't be alarmed at how difficult some of it might be, but just focus on the parts which are important, right? That was like the COVID era, and then afterwards there was Hamid, which is when I did it, which is 2023. 2023, I think, is the hardest fucking exam I've ever done. Where he did a beam column for question 1, and then question 2 was connections. So part A is like bolts, and then part B is welds. They're not particularly easy either, but 80 marks was weighted towards beam columns. Not only that question 1, the beam columns one, was a fucking custom section beam column. So it was like you had to work out everything by hand. You had to work out like ZE, you had to work out everything, right? So if you see a custom section in your exam, you'll know you're cooked, right? Unless it's like a pretty easy thing. But most of the time, and in all the other exams I've seen, it's not a custom section. It's just look on one steel, find all the standard sizing, just know where to look. Things like that, right? 2024, which was last year, Brian's exam. Very easy. I can actually show you. Probably can't show you. Okay. Yeah, like basically it was something along the lines of question 1, design this for tension. Question 2, they give you like a welded beam or something. It's like question 1, tension capacity. So say it was like a 1000 WB something. Tension capacity, compression capacity, and then it's like assume like these things like L, E is whatever. 3, flexure. 4, what do they do next? Like I think bolted connection. Flexure, they'll give you a bit more information like LE, whatever, alpha, M, whatever. Question 5, I think it's like shear, or maybe it was like 5 was bolts and then 6 was shear capacity. It was almost like an assignment style question, like one of the assignments you guys have done recently, where they didn't really tell you anything about the external loads, and it was all just based on like how strong is everything in just its capacity. So like it was really easy, and people walked out of the exam like really happy because it was quite easy. But I have a feeling because like Brian kind of saw like the bell curve was skewed towards like the HT or like distinction kind of range, he's probably gonna make it harder. So what I'm gonna try to go through today is, yeah, it's a 2021 paper, yeah, it's from ages ago, but it hits all like the key topics. So it's got like tension, compression, bolted gusset plate, flexure shear. And if we have time, we'll kind of run through a beam column question as well, if possible. But that one's more about steps. You know what I mean? Okay, any questions? So yeah, there was a lot of like context for this course, which I think is important. But yeah, so if we're all on the same page now, I'll just get started. So here's what the 2021 exam looked like, right? So I think this is different to the one that you've been provided recently. That one was like 2020 or 2019 or something like that. So firstly, okay, you're looking, you're using your reading time. You've got 5 minutes. You're like, fuck, I haven't done a truss since like 1300 or something like that, right? So that's the first thing I'll probably revise. If Brian's gonna make you find out like external loads, find out how to get the tension and compression in members. There's like a lot to take in. So all of these kind of have different cross sections. This one's double PFC, this one's double PFC. This one's double equal angle. So that's the double equal angle cross section. This one's the double PFC cross section, right? So immediately you're like, okay. It also gives you details on like how the bolts are arranged. Now, why I say it's hard, right? Because nothing about this is particularly hard yet. Failure of tension member. Where it gets hard, and why it was like a COVID question, is it's all algebraic. So you had to solve things like, what is the maximal allowable live load, which can be, pulled down at this point, given this dead load. So you can imagine like it's a lot harder when you don't have a set value. You have to like find that threshold value. Yeah.
That's actually the example we provided for it.
Oh really?
Yeah. So that's 2019 and 2021.
Oh.
Numbers are switched around.
Oh okay.
Yeah, but it's pretty much the same.
So lazy.
Yeah.
Okay, sure. Now I want to put a fat disclaimer out there. Like, I just fucking did my best for finding the solutions for this. They're not verified because he doesn't give any answers, right? But it should give you the right steps and ballpark. Now the bolted connection, that's the only thing I'm not sure about. I think everything else should be correct. But I'll run you through my thought process for everything, all right? So firstly, okay, we're still using reading time up, okay? There's like POV here in the exam, right? So, okay, sure. I kind of get everything that's going on here now. Cool. Question 2. Find the failure of the compression member in the previous figure, right? So, okay, question 2 relates to question 1. All right, fair enough. So now we're doing the exact same thing, but now we're finding the limiting PQ, like the live load, for the compression member, wherever the compression member is. Like, we'll find that in a second, right? Question 3. Find the failure of the bolted gusset plate connection, which PQ can allow. So now we're talking about, okay, this is the bolted gusset plate connection. What's the maximum value before those bolts all fail in shear, right? So, okay, we were like, okay, this is all like related. Question 4 is different. Now, question 4 is like a different situation. We've got like a continuous beam with two spans, and we have we're basically designing for flexure and shear, right? It says both limits of flexure and shear need to be checked. Now, same thing. It's hard because it's algebraic. It's hard because you're solving for like an unknown the whole entire time. Now, if you want to turn this into a practice question that you can do by yourself, you can just plug in some value for like PQ or WQ, and then it just becomes like a normal question. And then you can try to solve it that way. But we'll just do it the cooked way, because why not, I guess. And yeah, so that's the whole exam paper. And when you have the algebra to rearrange for like the unknown, it just becomes like so much harder, right? But that's, so when you're looking at any of these loads, right, let's just call it R. So that could be V, that could be moment, that could be axial capacity N. What we're saying with the capacity equation is that all that like weird shit going on with PQ is on the left-hand side. It's all the external loads happening. When I say capacity, that's the right-hand side. That's stuff which is always going to be the same if he gives you what the section looks like on one steel, right? You can look on one steel, you can be like, okay, we have to do it for a 410 UB or something like that. That's all here, and it gives you like the grade of steel, for example, right? That's all separate. So capacity is one side, you do that separately to the moments, the forces acting on your structure. And so if you are given something like this cooked, right, and you can see that, okay, it's the left-hand side of this equation that's going to be really, really hard. Say I don't know how to do that. Skip it, just do the right-hand side. You get all the marks, right? Except for like not getting the final answer, but you know what I mean? So this is kind of how this exam is set up. And now the reading time's over. And we're like, okay, we have to actually do this question now. So, okay, there's a lot going on, and it looks a little bit different just because in 1300, we focused on these as if they're like lines, right? Like we don't really care about the cross-sectional material properties of them. We just did that. And then in solid mechanics and all that, and this course, we start talking about like, okay, what's the cross-sectional capacity? Like we start analyzing the cross-section a bit more and all that stuff. And you're like, what do I do first? Like how do I marry these two kind of concepts together? The first thing I would do is do your Eng 1300 truss analysis. That's how you're going to find your external loads, okay? When you look at the cross sections and stuff, that's solid mechanics, but let's just say it's from this course. That's how you're going to find your capacity. Let's call it NC for compression, or like, you know, NT for tension or whatever, right? Got it? So we analyze these separately. We can completely do them like as two separate kind of things. So let's start with the truss analysis, okay? So I've just redrawn the truss. That's the free body diagram. Just by looking at this, right? So I'm going to draw the force on. So this was PG is 30. I think it's 30. Yep. And then PQ is unknown, yeah? Assuming that PQ is positive, right? Just think about how this shape is going to deform, right, in space. I'm also stalling because I'm pulling on my nose. Let's just think about that for a second, okay? So if you thought that it might do this, where, okay, this point is pinned. It's pinned in the X and the Y direction. It can't move. Okay, this point's a roller. This thing can roll up and down, right? If there's gravity loads acting on it, it'll probably roll down, right? This one here is I'm gonna exaggerate it a bit. So remember AC is gonna elongate, right? It's gonna elongate because that force wants to pull it down, right? And then BC, oh no, not BC, AB is gonna wanna shrink, right? It's gonna wanna shrink because it's kind of like pushing in together. So now we've kind of already identified the tension and compression members, right? Like just by doing it in your head, like step by step. So if you get the wrong answer in your truss analysis, you're gonna be like, hold on, this is sounding off alarm bells. I should just look at my numbers again and see if I got a sign mixed around or something like that, right? So you would expect to see tension in this diagonal member, and you'd expect to see compression in this member. This one, I haven't like done the problem, but I'm pretty sure it's tension. Like the thing is about that one is it's not going to be the critical one. Yeah,
I'll just say it like that. Okay, cool. So let's do. Let's analyze node A. So at node A, here's what we got going on, right? We have an unknown, AC. We have an unknown, AB. We have force PG and PQ, all unknown. Now, when we do method of joints, right, we basically turn this into a particle. There's no moments going on because everything's pinned. All the forces are coming off of it, no eccentricities or anything. So in this trust node, everything is only based on forces and not moments, okay? So with that said, we can't, like, there's no use in doing any sum of the moments, right? That's not going to get you anywhere. So we can only ever sum the forces in the vertical direction and sum the forces in the horizontal direction, right? So given that we only know stuff about the up-down direction, right? There's no point in going left and right because we have too many unknowns, right? So we want to do the sum of the forces in the vertical direction, right? And so now I'm just going to write it so that anything that's positive, right? Any arrow that's going up is going to be positive. Any arrow that's going down is going to be a negative, right? So we know this is going to be negative P. Well, I'm not going to split it into PG and PQ yet, right? I'll just call it P, right? And we know that some portion of AC is going up, like this part of this arrow, okay? So the thing about this arrow, let me just expand this out for a sec. The thing about this arrow, and because like the truss geometry, right? We know that this is 45 degrees, right? You can work that out because of, 4 meters by 4 meters, that's 45 degrees, right? This angle's 45. When you have a force vector, right? You can split it into its x and y components, right? Let's call this ACY, ACX, right? You can split it, right? The way you split it is essentially, what I'm going to do is going to be a bit weird. And I know what I'm going through is quite basic, but like people haven't done trusses in a while, so I just want to explain it. Right angle triangle, right? 45 degrees. We want to solve for ACY, okay? ACY. We know sine of your angle is opposite over, this brings you back, eh? Opposite over hypotenuse, right? And so, okay, what's the opposite of that sine 45? Opposite is ACY. Hypotenuse is AC, right? Rearrange AC sine 45. That's how you find that vertical component of that force. Get it? I'm going to leave that down here because some people are still copying it down. So, with that said, the arrow that goes diagonally, we just want that vertical component of it, which is a smaller component than the diagonal, right? That's going to be AC sine 45, right? That's all the stuff which I'm going to raise in a second. So copy that down if you want. And that's all equal to 0, right? We want to solve for AC. Why do we want to solve for AC? We want to find how much tension is in this member, right? So AC is the tension in that member. It's the axial force that's going through it. Now, while you guys are copying that down, I'm going to explain the logic behind method of joints a little bit more. So with unknowns, right? We have an unknown in the member AC. We have an unknown in the member AB. I know I just said that whole thing about like the truss deforming and then that one's in tension and that one's in compression. With any unknowns, just assume they're in tension, and if you get a negative number, they're in compression, right? Like, don't flip this arrow and start confusing yourself. So don't write it like, I know that's in compression because like la-di-da, that's like the way the arrow goes. Just do an arrow that points away from the node in tension and give it a negative magnitude if you have to. That's the best way to not screw up the numbers, basically, especially when you have to do a lot of nodes in the method of joints. Okay, we all following? Yeah? No? Okay. So here's the thing. AC. The thing about our external force P is that like P was basically has two subcomponents, right? So we want an expression to find the amount of G in our diagonal truss member, and we also want an expression to find the Q in it. So we're just going to write it as two separate expressions. So it kind of like diverged. You can think of it like that, right? Oops. That is equal to PG over sine 45. And this one was given as an actual number, so that makes things easy because now we actually just get a value. So that's the amount of dead load that causes tension in that member, right? Now for the live load, what am I doing? For the live load, it's a little bit harder because now it's an algebraic expression. We have PQ like we had for PG, except PQ can't be resolved yet. It is still a algebraic expression. And that's it. So that's all we can do with that right now. So that's what we have for the tension, like the dead load component and the live load component in that member, right? Let's put a pin on that. Now, think about the load combinations, right? We want to find the amount of tension in AC, right, when we express it as a load combination. The live and dead load case is going to govern basically, right? I guarantee you. You can do a dead load only case, but then it's going to be incorrect because, okay, getting too into it. Just trust me. This case is going to govern, right? This load case. It basically only doesn't govern when you have dead load only, essentially. Okay, so that means we plug in PQ, right? Where you see G. Oh, sorry. You plug in PG, where you see G there. And we plug in PQ, where we see Q. Now that's what we're working with on the left-hand side of that expression, right? That is the left-hand side of the capacity equation. Now we're flipping. We're going over to the right-hand side of the equation. We're finding out the capacity. Now we care about material properties. We care about geometric properties. We don't care about external loads anymore for the moment. So, just to recap, that's our tension member. We're doing tension design in question 1. Here, this section is made up of a double, I'll show you here, double equal angle, right? And do you know that cross section which, sorry, I'll come back to this in a second. This cross section here, the gusset, now that's only true for, let's see. Yes. Okay, good. That's the gusset, the rectangular plate. So we don't actually care about this gusset in terms of our calculations. Because let me draw it in 3D. That's one equal angle there. And that's the other equal angle there, right? The gusset only is in this portion, right? So for the majority of our tension member, it's going to be the weaker, like the smaller section, right? So we just take the smaller section as our actual cross section and tension, right? That's what I drew here, yeah? And so from one steel, we steal the gross area, right? For a single 150 by 150 by 10 equal angle, right? We multiply it by 2 since our cross section has 2 equal angles, right? We're told in the question, it's grade 350 steel, right? So when we go to one steel, let me see what I can do. Sorry, just give me a second. 150 by 150 by 10. We go down to the 10 row. We get the gross area in this column, right? But then for anything material property related, we scroll to the next page, right? This left half of one steel is 300 plus steel. That's not our grade of steel we're working with. We're working with this one. And I know it's just like a bunch of Australian standard numbers, but here, this is grade 350 at the end. So that's 350 on the right-hand side, yeah? What we do is we do the same thing. Was it 150? It was 150, right? 150 by 150 by 10 EA. We go to the left. We're looking for the yield stress here, right? Oops. Not only that, yeah. Well, I'll just go back to this and I'll show you. So that's for yield stress, but for tension design, we also need the ultimate stress, right? Oh boy, my computer's not liking this. Sorry, give me a sec. But he's row. Sorry, I shouldn't say row, column. Oh, this question didn't require initial sizing. So initial sizing is only when you're not given what the section should be. Yeah, so this was given in the question. So if you don't have to do initial sizing, you choose whatever sizing they give you. Yeah. Okay, basically, we go to this table in the standards, or from your lecture slides, and this is in order to find FU, right? This is grade 350 steel for a flat section, and we're looking for the tensile strength, which is 480. We're gonna need that to calculate the fast fracture capacity, right? So that's that right there. Cool. Okay, yield strength. Yep. Oh, okay. Let me tell you the secret, right? Two ways. One, go to one steel, go to the thickness of flange, or that's the slow way. The fast way is for an equal angle. That's your depth. That's your width. That's your thickness. Yep, it's code. So that 10 at the end is the thickness. So you can imagine as you increase in thickness, you get a stronger section. So that's how they do the products. So you see a 200 by 200 by 12 EA. It's 200 deep, 200 wide, 12 thick. Yeah. Okay.
Wait, sorry, what was it? I thought that was the way. What was the slow way?
Oh, sorry. The slow way is you go all the way.
That is like the way that you find that.
You can, but the slow way is you go to the table. What fucking loads. You go to the table, and you're like, what's the thickness of a 150 by 150 by 19 EA?
Oh, okay.
Oh, right, it's 19. Right. Yeah.
Okay, wait, so there's like slight differences because in that table, like the 16 one had 15.8, whatever. But I'm guessing that changing.
Yes.
Why is
Because
that?
so the steel products aren't exactly always so like a 610 UB, right? Let me draw it up on this.
So it's like if we just, for example, took it from the name. Like
Yep.
The name.
Yep.
But like we didn't bother looking at the
Yep.
text, does
Yep.
that affect our results too much?
No.
No.
That's the main thing. But yeah, like a 610 UB is not exactly like 610. It's like 612 or something like that. Depends on like the exact product you're looking for. But it'll give you the correct ballpark. And it'll give you, yeah, it doesn't matter, basically. It won't matter, yeah.
That's
Okay, so yield strength. Come on. So yield strength for tension, right, relies on two things. Your gross area and your steel strength, your steel yield, right? we've gotten both those things now. So this is just plug and play. Right? Get that. So in terms of units, right? I'm gonna start skipping steps for units later in this crash course. But if we have MPA, right? We have mm to the power of 2, right? MPA are newtons per millimeter squared, right? You have millimeter squared, newtons. When you multiply them together, you're going to get newtons, right? Now, most of the time, we like to present things in kilonewtons, right? Because we do external forces in kilonewtons. Like we say, oh, there is 30 kilonewtons of dead load acting down at this point. We do it in kilonewtons, it just is a cleaner number. So when you're trying to communicate between the external loads and the capacity, we generally want to keep it in kilonewtons, right? Okay. Fast fracture. This is just a different failure mode in tension. It has a different equation. So KT is a correction factor. I'll come back to that. AN is your net area after removing the bolt hole area, right? And then FY, oh sorry, that's not FY, that's FU. Excuse me, excuse my French. This is 480, so it's a high number, right? So let me just quickly go back to the cross section, right? Show you what's going on. So these are M20 bolts, right? Correct? M20 refers to bolts that are 20 mil wide, right? On our cross section, they look like this, correct? Because we're looking at it as a cross section like that. So even though there is another kind of like parallel set of bolts over here, we don't care about that because we just care about the section, right? On this diagram you can see, because it's a double EA, there's an equal angle on the other side, right? That is shown on this cross section there, right? So when you draw it out like this, visually you can kind of see the area you have to subtract in order to get AN. AN is the net area after you remove the bolt hole area. Yep.
Do you do it for both or one and then double?
Up to you. I did it with both. So I did AG as both of them combined, which I think was that, and I subtract four holes basically, right? But you can do a single one, subtract 2 holes, multiply by 2, same thing, right? Okay, so let's look at these bolt holes. The bolts themselves were 20, right? We said 20 bolts. What we say is on either side of the bolts, there could be an installation error or a bit of wiggle room because of where the threads go in, right? So you have 1 mil on either side of that, which you increase that whole diameter by. So we just add on 2, right? So if you have M20 bolts, 22 mil for the whole opening. In terms of the thickness, right? Does anyone remember the thickness thing we just talked about there? Perfect, 10. 10, so since our equal angle was 10 wide, that's that entire like rectangle is what we're scratching out, right? And we do that 4 times. Okay, I'm gonna scroll down. I'll redraw it. Okay, I didn't redraw it that well, but I'll redraw it. We're doing this, right? So that's 22. Well, I'll just do 20 plus 2. That's 10. And we got 4 holes, right? So AN is AG minus 4 lots of 10 times 22. Right? That gives us, what does it give us? 4,700 millimeters squared. Okay. Cool. So now NT is 0.85. Okay, let's talk about the KT factor now, right? So first we'll talk about tension. So basically, we got up to this part of the crash course, and now I'm in editing, now I'm in post. And I wanted to explain KT a little bit better. So KT is the correction factor
for fast fracture, and all you're really given in lectures is this kind of these scenarios, right? And you're told that KT is 1 when these situations that you can see, which have been highlighted, is true. Usually when it's like symmetrical, right? KT is not 1 in most other scenarios which are listed here, right? It's to do with the symmetry of the section and whether it's loaded uniformly in terms of its stress and whether there's an eccentricity happening. So if there's any kind of eccentricity in that load or any kind of non-uniform stress distribution, KT is not going to be 1. So what do I mean by that? If you go to where you download the Australian standards from and you look at the supplementary, so there'll be the regular one download, the AS4100, and then there'll be a supplementary text. The supplementary text hasn't been updated since 1999, but it does help to explain. It has some like nice graphs in there sometimes. It helps to explain parts of the code which aren't really talked about in depth or explained why otherwise. So it's a commentary basically on the standards. So here's what it says. What it says is kind of what I just said earlier, but it helps to visualize it. So here's looking at the section as a cross section. These are just various examples. So this one's like a equal angle being welded onto another member, for example, like a plate. Here's what it would look like side on elevation view. And here's what the the stress distribution looks like, right? So this is uniform and it's in tension, right? Here we have a scenario where eccentricity is affecting it. So the force is being applied off center, right? This is the eccentricity effect. And that's when you get stuff like KT is less than 1. Right? So before we had KT as 1. Now when you have eccentricity, it's like that. Here, KT is 1 because it's uniform and is no eccentricity. Here there's no eccentricity, but it's not uniform anymore. This is called shear lag. So shear lag effect happens for when it's basically just describing this phenomenon of non-uniform axial stress distribution in tension. So yeah, this one is another case where KT is less than 1. So I just want to add that in. Yeah. Right, when they're double, they become symmetrical. So KT is 1. That's 4,700. This is 480. So now I'm going to skip the step of converting it from newtons to kilonewtons, and I'll just go straight to kilonewtons, right? Because of what I said before. So when we're looking at the difference between 2008 and 1917, right? Which number are we going to choose? Just logically, we're dealing with capacity. We're going to choose a lower one. So whenever we're dealing with what is the strength of our member in tension, like you want to under exaggerate it, right? So you want to choose whichever one's going to fail first, which is the lower capacity, right? So this is the lesser number, so we're going to go with that, right? Okay. Now, backtrack. Our load combo looked like this, right? You can probably imagine what we're going to do to solve, right? Our phi, 0.9, the value we take is 1917.6. We basically have to rearrange for PQ. I'm not going to write it out, sorry. But we get this number, right? So here's where I kind of got stumped and I had to like double check my working and stuff like that. It's just because these numbers are like a bit strange. So if you think about it, right, we have a truss. This was 4 meters. This is 4 meters. We had a force that was pulling here. PG is 30, right? If you're saying that PQ is 790 or something like in that magnitude,
you're like, wait a minute, that can't be right. You're going to be like, that, like, I've surely got a wrong number or whatever, right? The thing is, our section is quite thick, right? So double PFCs and double EAs, there's actually quite a lot of meat on that, right? The second thing is that tension usually doesn't govern. Compression's a lot worse because of you have your member length and then it can buckle and things like that, right? So tension's actually going to give you quite a generous external load, right? So in this question 1, yeah, like we've checked for tension, but and it should be ridiculously large because it's not going to be governed by tension. It'll be governed by something else. It'll be governed by like compression or something like that, right? So just keep that in mind. That was like my initial thoughts when I got this number, but I'm pretty sure it's right. Okay. Any questions? Cool. Moving on. Question 2, compression, right? Similar process. We have that node that we're analyzing, but now we look at node AB, right?
So just quickly,
Yep.
so the reason why we knew which member to kind of solve for was weak is because you kind of just looked at it and thought, well, like if you're pulling it down like this member should be tension,
Yeah.
this one should be compression.
Yeah.
So that's kind of how that first question you have like that, it's going to solve out
Yeah,
for tension at the beginning, right?
pretty much.
Okay.
Yeah. Yeah, fine.
On the one still.
Yeah. Yeah.
It says T is 9.5. It says 10.
T is equal to 9.5. Oh yeah, so same thing.
Yeah, I asked.
It's basically it doesn't matter because the only thing that thickness actually determined was which range of yield strength that we care about, right? So it's gonna be the same ballpark, right? As long as it's less than 11, it doesn't matter, right?
Oh yeah.
As long as you're using the AG value provided in one steel, it'll be accurate because that AG accounts for even like it'll account for the fillet and everything. That AG value in one steel. So if I drew this more accurately, it would look like this. It also accounts for all that like fillet and shit like that, right? So just use the value in one steel because it's going to give you a more accurate number than trying to do it by rectangles. Sorry?
The one still says 9.5.
You meant this, right?
Yeah.
Oh, we're taking
Yeah, you just take AG. You don't have to calculate AG by hand, right? Okay. So, wait, just going back to that question real quick. So, you know, in your assignment 1,
Yeah.
it looks like this, right? You should be able to just look at this and be like, I kind of know which member's going to be compressed and which one's going to be in tension. Be like, these ones will be compressed, that one will be in tension because of how this shape will kind of deflect, right? Yeah. So, that's the idea. Or maybe not that, maybe like that. Yeah. So your understanding of trusses will help a lot when you're doing like tension compression kind of questions. Okay, so that was everything for, so this was just basically what I wrote earlier for AC. The reason is we need to know all the forces acting in AC in order to find what is happening in AB, because now we're going to do some of the moments in the other way, in the horizontal direction now, right? Okay, so let's follow the direction of the arrows. So if the arrow's going left, we subtract it, yeah? So both these arrows are going left, correct? But the difference is AC is acting at an angle. Right? So if we solve for AB, AB is going to be a negative magnitude of something to do with AC, whatever. That makes sense because one has to be in compression, one has to be in tension to balance out, right? So now we do the same thing. We're going to split AB into its G and Q components, okay? It's dead and live components. So all I've done is I've subbed in ACX. Wait, no, X. What the hell am I smoking? ACG, right? Which was this constant, right? And now this time we're going to sub in the unknown, which was ACQ, right? So these simplify to be a bit nicer than what I've just wrote, so I'll just write it down. This one's negative 30 kilonewtons in compression. This one is just negative PQ, right? Because essentially these two will cancel out. So those two don't cancel out if you don't have a 45-degree angle, but sine 45 and cos 45, type it on your calculator, it's the same number, right? That's also in compression, right? Okay, now focusing on the left here, 1.2 G, 1.5 Q. Wherever we see G, we plug in our compressive dead load. Wherever we see Q, plug in our compressive live load. Got it? So that's external forces done. Now we're going to find the compressive capacity, right? So now we're looking for kind of different things in one steel. We're looking for KF, which can be found for your shapes in one steel. We're looking for, the thing is, right, generally for compression we say we take AN as AG. Now in the code it's written as AN. All the lecture examples, all the workshop examples, they'll tell you to take it as AG. And in industry as well. For FY, so we have to refind it actually, because, sorry, I know you guys are copying this. I'm just gonna scroll back up. Our tension section looks like that. Our compression section looks like this. They're different. So instead of double equal angle, we have double PFC, right? So two channels kind of back to back on each other, right? So it's gonna have a different area, as you can imagine. It's gonna have different properties. Same grade of steel though. So when you're dealing with, I'm gonna pull up one steel again. We're doing parallel flange channels, and it was a 180. So yeah, we can find the gross area there and all that. The thing is, before we were dealing with equal angles, right? So you didn't have to differentiate equal angles by flange and web. Now we have a flange and we have a web, right? So if you guys have no clue what I'm talking about, let me pull it up. Say an I-beam, right? I'm gonna compare it with an I-beam and a channel. Your web definition is based on the area of the thinner width, right? And that's your flange. Same thing here. That's our flange. And that's our web. So for channels and for I-beams, we have two flanges and one web, right? So when we say that, you know, we have a certain flange, what do you call it? Yield strength and a web yield strength, we just take it as the minimum for both of them, right? You're gonna find that the thicker your section gets, the lower its yield strength gets. So imagine like you pour like a meter by a meter by a meter, so like 1 meter cubed of molten steel, right? And you just let it cool, right? And you're trying to use this structurally and all that crap. Do you reckon that that's all gonna evenly be cooled? Probably not, right? So that's the idea with when you have something that's thinner, it's gonna have a more consistent yield strength. You have something thick like that, its yield strength can be crap because it didn't cool properly, basically, right? And so that's where you get differences in like this and this based on the thickness. So the thickness of the flange and the thickness of the web are different. Got it? Anyway, we'll just take the minimum. So it's 340, right? KF. I might quickly explain KF. KF is one of those things that's incredibly aids if you have a custom section, but it's so easy when you have... Am I looking at the wrong one? Grade 350? Sorry, I was looking over here, wasn't I? We take the minimum, right? So 340. So KF is basically to do with how much of your section is going to locally buckle in compression. Now they specifically manufacture these products so that they get full utilization of the amount of steel that you put into it. They've kind of been like converged, like min-maxed kind of products, right? So they're obviously not going to give you something that's designed to have a lower form factor. Do you know what I mean? So you can trust that most of the time anything you get grabbed from one steel is going to have a form factor of 1, right? It's not going to locally buckle. So yeah, that's all the stuff that we had to grab. Yeah, so we just plug in that. We get 1 for KF. We get the area. We get the yield strength. And again, I'm just going to jump straight to kilonewtons. That's our section strength in kilonewtons, right?
Is that 5320 after you multiply energy by 2?
5. Yes. This one, yeah. So that's for 180 PFC. That's for 2 PF, 280, 180 PFCs. Yeah. So that's section capacity done, right? I've got a little like demonstration thing here, right? So we have, here's like a piece of wood basically, right? But I'm gonna just pretend there's a truss member that's in compression, or if it's in, like if it's a column or something like that in compression. So in tension, right? If I pull on this, basically the length of the actual thing has no contribution to whether, like how strong it is basically, right? So that's why you get cables and like cable bridges which span for like 100 meters or whatever, right? Cables like are just purely in tension. The length of them does not reduce its strength, right? Compression's different. So you can imagine, right? If I press down on this, it's gonna start to buckle, essentially, right? And so, okay, say I had the same kind of material, like a wood, that's like this short instead, right? Instead, it's not gonna buckle. It's gonna purely be based on a yielding, like crushing kind of failure, right? And same thing if I had a stick that was the length of this whole room, right? I push down a little bit, you're gonna see major buckling effects. So that length, right, is gonna have a kind of quadratic effect on how much strength we have, because it's gonna be governed by buckling now, right? So now we're just calculating buckling constants, right? So alpha B, this is like kind of a material and like how you produce your steel constant, right? So there's a bunch of different ones. I know I just erased the answer. Have a read of this. So this is a table if your form factor is 1. What value of alpha B do you think we're going to take? Yes, it's 0.5. So if it was an I-beam, it would be a hot rolled UB, so it'd be 0. Since we're dealing with a hot rolled channel, it's going to be 0.5. Now, if I just quickly go to one steel again, right? And I go to the very start. One steel company produces hot rolled products. So that answers your question if you had it about what, like, is it hot rolled? Is it cold formed? It's fucking hot rolled, right? If it's from one steel, basically, right? So yeah. But yeah, hot rolled products can still have different values based on the type of section it is, right? Okay. Oh, the other thing is, like, a lot of the time, if you're given a custom section, for example, in your finals, right? It's like, okay, we're gonna try to make like a welded section like that or whatever. It'll be welded, right? Welded I section, right? Welded box section, whatever. The other thing is that, okay, you know what? Put a pin on what I said earlier about these, right, in one steel. These are hot rolled products, but these are still welded products, right? They still have welded beams and welded columns. So that will override what I just said, right? So if you're given a WB, you're given a WC, now these become welded products. Got it?
So it's like our assignment. Well,
Yeah, your assignment was made from welded plates. Actually, just think about why welded beams exist to begin with, right? The biggest UB you can find is 610, right? Obviously, it would be like a bit bigger, like 612 or some shit, but just say 610. 610 is like, it's like that, right? That's like 610 millimeters. That's the biggest beam that comes in a standardized size. What happens if you have like a huge building, like or huge bridge or something that you're gonna need to build, right? You can't just be relying on tiny. They're actually quite big, but you can't be relying on 610 UBs, right? 610 UC, yeah, you know, that kind of shit, right? Welded beams, the smallest they come in is 700s. You only need to go through the effort of making a welded beam if you need something bigger than what the standardized universal columns and universal beams come in, right? Okay. Any other questions before we move on? Okay. Head in the game, guys. We got compression. So, what I've done, this is the exact same question as the compression question. I've just repasted it because I want to highlight something here. The truss is considered as pinned with respect to buckling out of its plan, and the gusset plate has a thickness of 10 mil. Okay, that's important, right? So, okay, well, the gusset plate thing we'll come back to, but what it's telling us, okay, firstly, we have to find for our modified slenderness ratio formula, we have to find effective length in compression, right? Now, the effective length formula is KE. KE is an effective length factor. We multiply that factor by the length, right? Now, if a truss is pinned on both ends, which every truss in the world is pinned on both ends, KE is going to be 1, right? So, and a truss is naturally a brace system. Yes. So basically what I'm trying to tell you is K is 1 for a truss, right? For L, that length of that compression member is going to matter. I'm going to have to scroll up to it again. Oh no, I think I have it here. It was 4 meters, right? So remember, that was that member there. Because it's 4 meters by 4 meters. That member's 4 meters, so yeah. So the length we're going to take is 400 mil, basically, right? 4 meters or 400 mil? 4,000 mil. Okay. Now I want you to think about something. Basically, our slenderness is going to be governed by our slenderness in the X and the Y direction. Now, this might be, like, if you know what I'm talking about, like, yeah, you either know it or you don't know it, right? So, essentially, focus on this rectangular wooden cross section for a second, right? I'm going to draw it as well on the screen. This has a very clear major and minor axis, right? So the idea is that the major axis bends this way. If I tried to bend it this way, it won't even really bend at all. It's quite stiff, right, in this major axis direction, right? If I bend it this way, it's on the side now. If I put axial compression on it, right, it's gonna be less stiff, right, in bending, in buckling, I guess. So what this tells us about this shape, so not to do with the shape of our of our question, is that our slenderness will be governed in the Y direction unless we have heaps of restraints stopping this from buckling. Okay? That's an extreme example, but yeah, just keep that in mind. So basically, remember our section looks like this. So those are 180 PFCs, right? The gusset plate in the middle, they told us, was 10 mil thick, right? 10 mil. But we're not going to consider it, right? We just know that gap is 10 mil. Okay. So now, assuming that the length is not restrained, right? Which it's not because it's truss. Is it gonna buckle about the AA axis or the BB axis, most likely? Yeah, put your hand up if you think it's A. What's the minor axis? What's the minor axis? Is it gonna want to bend? Like looking into it, is it gonna buckle like that way down, or is it gonna buckle to the side like that?
Down.
So AA, is that what you guys think? Yeah, it's AA. Very good. So I probably didn't draw it the best in terms of the dimensions, right? Let me draw the dimensions out for you. It's 180. This is 180. This is 10. Oh, jerks. That's 180. That's better. This was 75. Okay. Our flange width, our flange thickness, I should say, was 11. Our web thickness was 6, right? Which leaves the remainder of this length as 69, because 75 minus 6, right? Okay. So you guys said it's gonna buckle about this axis, right? Should we call that the YY axis or the XX axis? I would call it the YY axis. So this is weird because this is not the way that you normally see it, right? But essentially we've kind of rotated it 90 degrees from its strong axis. Does that make sense? Because normally we would expect to see XX being orientated like this. I've just kept it like this. That's fine. Okay. So by the way, these numbers here, 6, 11, from one steel. One steel can give you TW, it can give you TF, right? So flange, 11. Web, 6, right? Okay. What we have to find, okay, let me tell you the rabbit hole we're going to go down right now, right? So we want to find the slenderness in the weak direction, which is YY, right? How do we get that? We need to do this. Okay, sounds easy. Oh shit, we have a double PFC. We can't just get that from one steel. We have to find the moment of inertia ourselves. The radius of gyration in the y direction is moment of inertia in the y direction over gross area, okay? See what I'm saying? It's getting cooked, right? So now we pull out our solid mechanics,
Oh my god.
right? Pull out our solid mechanics. Call this shape 1. Call this shape 2, right? And we're going to have to find IY. So I'm going to do 2 lots of everything. So 2 lots of everything because there's 2 PFCs, right?
Can't we just find one and done?
Yeah. That's what I mean. Yeah, 2 lots. Yeah, I put a 2 and then a bracket which says everything for a 1. Here's the moment of inertia for a rectangle, right? We're doing this for shape 1. Okay, alarm bells, right? BD cubed on 12. That shouldn't be for IY, correct? Not necessarily. Because we've orientated everything 90 degrees, right? We've orientated it so the y-axis cuts through horizontally. So when I say B, I'm referring to the left-right dimension. When I say D, I'm referring to the up-down dimension. So this should still check out. We're still taking it about the minor axis. We're still taking everything relative to the minor axis, okay? So there was, as you can see, there's 2 lots of shape 1. There's 4 lots of shape 2. There's 1, 2, 3, 4, right? Of number 2. We also have to do 2 lots of the parallel axis theorem shift for shape 1, right? So what I'm saying is, how much do I have to shift this shape up from the centroid, right? We shifted up that much, which I've called D, right? And then 4 lots of shifting for shape 2. We have to shift this from the centroid 4 times, right? Okay, are we all kind of following? Yes, no? Maybe we've lost some, yeah? Okay. So, for this shape 1, our width is 180. Our depth is 6. For shape 2, which is our little like flange element, the width is, what is it? 11. Our depth is 69 cubed. Our parallel axis theorem shift, we're doing the area, which is 180 times 6, same as here. And now we just have to think about how much we shift it by, right? Remember, this opening between the 2 parallel flange channels, right, was 10, right? So we go up by 5, and then we go up by another 3, right, to reach the middle of that shape. So the amount we shift is going to be 8 mil squared, right? Because that's the formula. And then we also have 4 lots of the other one to shift. We have 11 times 69 times, from neutral axis to the, for the opening, I shouldn't say neutral axis, from centroid to the end of that opening, that's 5 mil. The entire web, 6 mil. Halfway up that element, 69 on 2. We add all those things up, yeah? We get that. So IY, 6.83 times 10 to the 6. Yeah.
For IY, isn't that B cubed?
So it's relative to your perspective, and as long as you have the correct dimension in terms of the solid mechanics, it doesn't matter what you call B and what you call D. I could have called this B, but I've just decided to call this B. Yeah. I've rotated it 90 degrees, so the y axis cuts horizontally, right? You're thinking of it relative to when y cuts like vertically, right? Yeah. So yeah. Yeah. So B is just labeled the way that I normally think of it, like as if I'm looking at it like this, but Y has flipped. So that's all that's changed. Yeah.
Hey, it's me again in post. So this is for when we get up to the compression part. Basically, I wrote down an incorrect number. So if you add up 5, you add up 6, and then you add up half of 69, whatever that is, you get 45.5. So I wrote 45.2 in my original video, which is wrong. So I'll just show you the effects of that. Let me pull it up. I'll show you the effects and the flow-on effects of this, right? So if you replace 42.5 with 45.5, what you'll find is this number, oh sorry, it was 6.83. It was. I did it a bit weirdly. Now it's 7.63, so it's increased, right? So it's actually increased more than I thought originally when I did the recap demo. So this becomes 7.63. What the fuck am I writing? And this increases our radius of gyration in the y direction to 37.88. It also will reduce our slenderness ratio, right? Because this becomes 37.88. We'll reduce this to 123.139, like that. So compare the purple line to the blue line, right? So it's changed from 140 to 130-ish. Sorry, 130. 123. You bounce up to that same line, you go left. Instead of 0.3, we have an alpha C of 0.37 now. So we have 0.37, this becomes 0.37. La-di-da. It's essentially changed our number from 300 kilonewtons allowable to 377.55. So that's significant, actually. That's more than I thought it was going to be. That is a 25% increase in the amount of live load, point live load that can be added, which, yeah. So, yeah, just wanted to add that in.
I'm not as confident with this question. This is the gusset plate connection, right? But I'll tell you my thought process, right? So when you have a bolt connection, there's basically two things you have to consider, or like two different types of problems you have to consider. One is shearing, so shear bolts. The other is axial bolts, where the bolts want to pull out from the hole, right? So, in this case, we have a force going down like this, which means the force will look like that. The bolts are orientated perpendicular to this force, right? And so when you see this force happening, it's going to want to shear. So the bolts will want to rip and like split in half, basically, right? What we care about is the number of shear planes, right? So that's the number of ways the bolt is going to resist that kind of shear action, right? In our case, because we have gusset plate in the middle, two equal angles, we have two shear planes. That's like kind of layers in between, right? Oh, sorry, that's kind of like lines in between the layers almost, right? 3 layers, 2 shear planes, right? Okay, so the problem with this question, and in terms of like PG, PQ, in my opinion, is we don't know the eccentricity. It doesn't give us any info on eccentricity from this force. So when you have a truss, right, you basically want to design the truss so that all the, like the node is essentially where all the trusses line up, and that's where all the forces are applied, so you don't have any moments, right? So assuming that, we don't know where the force exactly is applied because based on this drawing, right, we don't know how far away that force is, right? And so what's that's going to do is that force, if it's like eccentric, if it's like applied like kind of an offset, it's going to generate a moment in this bolt group. So this bolt group is going to have a centroid, right? So we have 8 bolts like this. It's going to have a centroid somewhere, let's say here, right? If the force isn't applied exactly at that point, we're going to have a moment acting on the ICR, right? Since we're not given any of that information, so that's what I make a note of here. I'm going to take a really unconservative assumption and say that we have some V star, right, which is the force, right? And the bolts take it equally. So there's 8 bolts and they take it equally. Now, in reality, that's not going to be what happens because of what I said earlier with the eccentricity. What's going to happen is the bolt that's the furthest away, probably one of these two, that's going to take on the most force per bolt, right? So it's going to be disproportionate in terms of the force, right? So it'll be more like this will take this much. I'm going to do it based on like size of arrow, right? it will be like at a moment, so it'll be like that, and shit like that, right? So those ones up there will essentially take on more shear force. It'll be like, yeah, there's formulas for it, and it's in week 8, but we don't really have any of that information. So, okay, what we can do is we can move on to the capacity side of the equation, right? We're told that the bolts are M20 bolts. They're grade 8.8, and they're snug tight, right? That will give us from a table of information. I'll show you the table. Sorry. So the 8.8 bolts, right? We have this much ultimate strength, right? Oops. And core area for M20 bolts, we have a core area of 225 millimeters squared, right? So that's what we take. We plug it all into this equation. This one's 830. This one's 225. Remember how I said there's 2 shear planes, right? So I'm going to draw that out again. We've got bolt. That's the equal angle. That's the equal angle. That's the gusset. We have 2 shear planes, right? And in the question, it says that the shear planes intercept where the threads are on the bolt, right? So if you think about a bolt, they're going to have different areas, right? The core area and the shank area, depending on where the threads are. The threads are like the spinny parts, right? It's going to have less area where there's spinny parts. But the question says, imagine the threads, like the shear planes can intercept the threads, right? So we have a shear plane here, we have a shear plane here or something, for example, right? Based on this drawing. Okay. That's that. Here is a reduction factor if you have 10.9 grade bolts, which we don't, so we don't have to reduce it. That's just one. This is a lap reduction factor. So if you have, essentially if you have bolts which are lapped, which we do, right? But let's say that we lap it quite a lot, and the lap is greater than 5 meters, I think it says in the code. We have to start reducing how much these bolts are all contributing, right? Because even though like they're in parallel, and then at a certain point, then they start to like contribute an uneven amount, right? So like this one might be contributing more, this one might be contributing more, the other ones might be contributing less, etc. Right? So there's like a lap reduction factor. Again, we don't have bolts that are lapped at like 5,000 or whatever it was, so we just have that is equal to 1. Okay, so
What was it?
sorry.
Oh, that was the shear.
Yeah, and N is the number of shear planes, yeah, that are intercepting the threads. So now we have the overall shear force, which is happening at that place, right? And then it's divided by 8 because we're saying that there's 8 bolts that all equally contributing, which they're not. And then VF is the capacity per bolt, right? 1 bolt capacity. Here's force on 1 bolt. So we're doing everything per like for 1 bolt. V star is load combination times all that. That's the shear force at that point there. And then yeah, we just set it equal to each other. So PQ is 1,000, which there's no way. There's no way it's 1,000, because when you start to account for what I said, like if there's eccentricity, there's going to be a moment generated. It's going to cause a greater amount of shear force at the furthest bolt. This number will go down significantly. So it shouldn't be this at all. But we're just not given that information, so this is the best we can do, right? Okay. Any other questions right now?
Why is it just physically enough?
With the
Oh yeah. So let me just go up to here, right? NN is the number of shear planes we have going on here, right? Specifically, it's the number of shear planes that intercept threads. There's I think it's NO, no, it's NX. NX means if it doesn't intercept threads. So if it looks more like that, and one of your shear planes intercepted the area with threads and one didn't, it would technically be NX is 1, NN is 1. But there's kind of like a conservative, yeah. But usually in the question they'll tell you to assume the entire thing has threads, because that's the most conservative way to do it, right? It gives you the least capacity because we have a smaller core area than we have shank area. Yeah. Yeah, that'd be good. Yeah.
I think Brian was talking about like this step, like a throwaway.
Just talking about it.
Yeah. I don't know what he was talking about, but
Yeah.
you're getting it down and seeing it why it applies.
I know before Brian, like the other lecturers just said, always take it as NN. Yeah, don't worry about like when it doesn't. Yeah. I would do it like that. Just assume threads because like that minor increase in capacity could screw you over in the long run, you know, like if you're designing it and there's legal consequences and shit. Okay. Any other questions?
So sorry, just like an explanation of the eccentricity. Basically, if we take into account the fact that there will be a flat moment generated, basically does that mean that shear force would be lowered, but like that moment would take up like the rest of that force? Is that what your
Shear force would be lowered.
like, so why would the shear force be lowered?
No.
If you count the...
Oh, so the idea, it's not lowered. Okay, the idea is if you have a bolt grip, right? Like this, and then you find the centers here or something, right? You want to find what the equivalent Fy would be this way, right? The equivalent Fy, so the Fy is just this stuff that's moved that way, right?
Yeah.
So that stays the same, regardless of where the bolt grip is. But now we're also going to generate a moment. So it's a combination of Fy and the moment that's going to cause a higher V star max. So what I'm saying isn't that the force will be lowered, it's that there'll be force as well as like a point moment pretty much at that point, which is going to have a higher net force, which is like your V star max basically. Okay, that's all we have time for, but I did also give you a beam column question to look at as well if you'd like. And yeah, that's got gamma method, moment amp, combined checks. Have fun. Alright, thank you guys. Oh, okay. Alright, so now I'm just gonna redo the Fletcher one because I kind of did this first part wrong. It has like flow-on effects basically, right? So, let me get rid of this. Okay, just, I know there's a lot to look at right now. Just focus on this diagram. Okay, wait. Focus on the diagram and the text. So I'll read the text. Determine the max uniformly distributed imposed action, right, which is WQ, which can be applied to the top flange of the entire beam, as shown in the figure. The beam is a 410 UB, so tell us the beam, we don't have to do any initial sizing or anything. With grade 300 plus. The shear force diagram for the beam under an nominally uniformly distributed permanent action of WG equals 2 is shown in the figure. So this is where I got it wrong. So I misread that sentence. I thought that meant that, actually no, that was fine. So that's the dead load essentially, right? I read this shear force diagram as the shear force V star graph, but it's only the shear force for the dead load, okay? Both the imposed and permanent actions are applied to the top levels of the top flange. Applied at the level of the top flange. The beam is fully restrained against laterally torsional buckling at these three supports, F, 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 right? The self weight, ABC so at the three supports ABC, and there's no lateral rotational restraint along the beam in the two spans. So we'll come back to that. The self weight of the beam is included in the value of WG, and the bearing capacity of the web can be considered as adequate. Okay, and we have to do flexural and shear strength checks. Great. So essentially, right, we're going to call these AY, BY, CY, right, at the reactions. And it tells us that the shear force goes up by 6 kilonewtons, which I don't know what it told us. Like, we can work this out essentially. But that also means that this shear force here is 6 because it's mirrored, right? Let's work out the reaction. So AY plus BY plus CY is equal to WG, which is 2 kilonewtons per meter, multiplied by 16, right? We know this is 6. Let's go to the 6. BY. I'm just going to speed things up by looking at my notes. Write down. It's 20 kilonewtons acting upwards, okay? Which means if it's 20, it goes from negative 10 up to positive 10, right? So that's just for dead load, right? Now, live load is a bit trickier because for our free body diagram, right, we have an unknown WQ. Now, we don't know what the shear force will be. We don't know what the bending moment will be, but we know that it will be the same as like the shape for the dead load. But how do we find that? It's a little bit silly. So there's some images you can look up online, or like some textbooks you can look at, which show you different loading arrangements and common values, right? So if you have like a simply supported beam, right, you'd know that M star is WL squared on 8. I mean, some of you guys might know that, some of you guys might not know that, but that's like a common value, right? Because it's simply supported beam. These values are like WL on 2 for the reactions, just shit like that, right? So basically, there's a similar scenario when you have a uniformly distributed load over a continuous beam where the two beams have the same span, right, like that. And yeah, there's like a uniform load over it, right, which is the case for WG and WQ, right, for us, right? So we're allowed to use these formulas that you can see on the left here. So we know that the max shear force, right, is going to be 5WL on 8. So that's going to be 5WL on 8. Now that W is going to be WG, right, which is 2, because we're looking at just the dead load case, right? That's going to give us, what have I done? Oh, nearly made another mistake. Sorry. So the formula I read was the shear force one, which we've actually already calculated. We care about the moment, right? So you know how I said a second ago that this here for a simply supported beam is WL squared on 8, right? So if you had continuous beam with 2 spans, what you'd expect to see for the bending moment is this, right? But if you just have to think about it, like, do you reckon that these bending moments in the middle of the maximum bending moments in those spans is less? If you think yes, you're correct. There's less of a positive moment, but the maximum moment will be over the middle support now. And the magnitude of that just happens to be the same as the middle for a simply supported beam. Now, when you get to more and more spans, like 3 spans, 4 spans, this number is going to change. So it won't be. But this might trip you up because we basically have the same value, but a different scenario, because that one will be negative, right? So this is a positive bending moment. These are positive. This is negative, right? This max bending moment is the same magnitude as the max for a simply supported beam, but it'll be negative instead. If that makes sense. Okay, so that aside, we're going to use that information to our advantage because sorry about that, WL squared on 8. We just change this to WG. We have 2, the span is 8. So we're talking about this, one of the spans here, right? We're not talking about 16 meters. We're just talking about the value, like this is all relative to one of the spans, right? And the equal span lengths. So that gives us 16 kilonewton meters as our max moment for just dead load, right? For live load, this is where I was trying to go with this, right? 5 WL on 8, right? 5 WQL on 8, right? That will apply to there now. And this would be, yeah, like our max shear for just live load. So we can replace 8 there. And so we just simply get 5 WQ, which will be our max shear for just live loading. We use the same formula as we did on the left there for bending moment, except we've replaced it with our unknown value of WQ, which we'll solve for later. So now this becomes 8 WQ, right? Next, we plug it in. So for WG, we get 2 WQ, right? So we're going to get 2.4 plus 1.5 WQ for our, this is our factored distributed load, right? And so we're going to do the same thing. 5, 2.4 plus 1.5 WQ times L on 8. So that's just 5. Let me explain that better. That was 5 W star L on 8, right? Which is the exact same thing that we used here, but we can do it for a factored one, right? So that's what that was. We simplify it, it gives us 12 plus 7.5 WQ. We're going to use that later. And that will be V star. Similar idea here. Sorry. So we plug in this, which is W star. And we get 8 times everything in that bracket, right? And this is our value for M star, which we will use later. Let's do it in red. Cool. Hopefully that makes sense. I didn't have to, like, in your exam, you don't have to draw all that. You don't really have to draw any of this stuff out. It's more just to show you how these things, you basically take 1.2 times whatever I wrote there, 1.5 times whatever I wrote there, you add them together, combine them, and that's where you get this bending moment diagram, which is what we actually need. So we need M star, V star, right? Okay, next we'll talk about section capacity. So this is a simple formula. The section capacity in flexure is ZE times Fy, right? So we care about bending on this beam about the XX axis like this, right? So we're gonna need ZEX. How do we get that? Go to one steel. When you have a standard object, a standard shape, you go to the 410 UB 59.7. So this page will show us dimensional information, which will be useful, but what we need right now is ZEX. So would you go over to the column which says ZX? No. So this is only the elastic section modulus. We need the effective elastic section modulus, which takes into account sectional properties such as the slenderness of our actual section. So if that made no sense to you, basically what I'm trying to say is instead of ZX, we're looking for ZEX, which is on the next page. So we had grade 300 plus steel. So we go onto the left-hand side here. We go down to 410 UB 59.7. We get 1200. So that's what we need. And we also get that Fy
is the minimum between 300 and 320, right? So we take 300 and this, we multiply them together, divide by 10 to the 6, right? To get everything in kilonewton meters, we get 360. That's for section capacity. Next, alpha m is a factor, is called the moment modification factor, right? And it depends on what our bending moment diagram looks like. Essentially, here's what we're going to do with alpha m, right? Oh, you should also do a quick sanity check here. Essentially, the idea is that, okay, let's not do it since it's algebraic, but yeah. Let's just do this for now. So, let's fix that up. Basically, if you have the relationship between MB and MS is a little bit interesting, right? The idea is that MB is our actual capacity. Well, once we factor it, right? That's the actual capacity of our entire beam. We're comparing that with our external moment, which is based on unknowns at the moment for our question, right? So how do we get to this? Well, first we have to calculate MS, right? Say, for example, your M star, your external moment, was 200 kilonewton meters, right? It takes 200, there's 200 kilonewton meters applied to your beam, let's say. So if phi MB, right, is 300, then we're safe, right? If it's 200, it's on the dot, but yeah, it's safe, right? If it's 199, it's unsafe and it breaks, right? The thing is, MS is an intermediate step which we do, which is the section capacity, in order to get to that resolution. If MS is 199, you can bet that MB will not be greater than it, right? So MB will either be 199 or less. So there's no point in calculating further if we know MS. The thing is about this question in particular that makes it a bit weird, which makes it so that we can't really check this easily, is that this is based on algebra. So it doesn't say anything about whether we can continue or not, right? So what we do is we just write it through to the end and then eventually find MB. Okay. So anyway, with that said, we're looking to find MB. MB is based on these two multiplicative factors with MS, right? This is a reduction factor. So when you hear the word reduction factor, that means it will only ever be 1 or less, right? The thing is about alpha M is it's a mod factor. Modification factors implies that it could be less than 1, it could be 1, or it can be greater than 1. So it could be any of those. If this is greater than 1, right, and this is, let's say, 1, what happens is this combination of alpha M and alpha S are going to be greater than 1. And so you're going to exaggerate what you're allowed, right? So if you have like a, imagine like you have this percentage bar, right? MS is 0. If you had this scenario going on of your multiplication factors, right, you've essentially crossed over your allowable bar and you have to set it back to that, right? You have to shrink it back. So that's a scenario which can happen, right? So you have to be careful on what the product of these two things are, because the product of these two things have to be less than or equal to 1. Okay, whatever. What it actually is, alpha M, is it gives you additional strength, or sometimes it reduces it in the cantilever case, based on how bad your loading is. So the worst case loading you can get for alpha M is a bending moment diagram which looks like this, like just a rectangle. How do you actually get that? You basically need your beam to have point load moments on both ends.
and this gives you an alpha m value of 1. That's actually the worst case scenario for alpha m. For other cases, right, like a simply supported beam with a universally distributed load, uniformly distributed load, alpha m is in the ballpark of 1.18, I want to say, something like that, right? So it's a little bit better than that rectangle, right? Once you do the calcs. What we see here for the 2 span with the uniformly distributed load is something like this, right? This results, you will see, in an alpha m value of 2.25. That's quite good, actually. Oh no, sorry, I think I got this number wrong. I think this is about 1.5. That seems more accurate. So 2.25. This just means it's better when it's a continuous beam in terms of its moment capacity. Now, alpha m has a cap. It has to be less than or equal to 2.5, right? So there's only so much it can help your capacity by before it has like no further considerable effect, right? Anyway, so we're gonna find that this is our scenario for alpha m, but let's see how we get there. So here's part of the table, right? And it's a little bit confusing, but the idea is we want to focus on this part, right? We want to work out beta m. Let's do it in blue. We basically want to work out beta m. So beta m is when we have our m star max, correct? So from that little textbook that we saw, our max hogging moment, right? So the negative moment at the support was WL squared on A. This has to equal to what we see on that graph there, right? Like that. So you can just see these terms all cancel out, giving us beta m is equal to 1, okay? So now we have a if statement, right? If beta m is between 0.7 to 1, we have to use this formula in order to find out alpha m. So this table is presented in a weird like order, but this is essentially what we have to do. We just use this formula. Like so. And we sub this out. This is 1. When you do this in your calculator, you get 2.25. So that's how you get alpha m is 2.25. Okay, next we'll do alpha s. So alpha m, remember this beam had full lateral restraints at the supports, right? And the symmetry on the other side. So the same thing will happen for the other span. The thing is, it had a detail which looked like this, I believe, right? Which is an equal angle restraining the top flange. Let me just show you. There was an equal angle. Here we go. Detail 1. There's an equal angle attached to a flexible gusset plate, which restrains the top flange from lateral movement, right? So why is that important? Well, we have to kind of unpack lateral torsional buckling a little bit, right? So basically, what have I done? Basically, right, imagine this is your I-beam, it's your 410 UB, and then we have a beam like this. I might just draw this smaller. Yeah, I'll draw it smaller. That's easier. Okay, we have this beam like so. Let's just keep it simple, we'll make it simply supported, right? We're gonna look at this cross section, which is what you can see on the left here. Okay. Basically, what happens as this beam gets loaded is that this beam is going to want to deflect down like so. And so you'll see this vertical deflection go down like that. When you don't have a restraint in between, right? What happens is once you let it enough, it's going to want to laterally torsionally buckle. So what do I mean by that? If you think about the shear stress distribution, as you bend it more, there's going to be a push-pull. There's going to be compression on the top flange and bottom on the and tension on the bottom flange. So basically imagine imagine a beam like this, right? These bottom fibers, as it's being bent, wants to pull apart like this, and these top fibers want to compress and go in like this, right? That's compression, tension, right? Simplest word beam. So once it does that enough, what happens is we know from our compression topic that the top part wants to buckle out in the weak direction, right? The weak direction of an I-beam is left and right. So the top flange, the compression flange, wants to go this way. The bottom flange is doing something different. So the bottom flange is in tension. It wants to pull like a rope, right? It wants to pull and straighten out. So what happens is this beam actually does this. So the bottom wants to stay in that axis in tension. The top is in compression and wants to buckle out like that. So that's lateral torsional buckling. Lateral means sideways. Torsion means twisting, right? Lateral torsional buckling. So how do we prevent this? So for compression, right, what we had to do is we essentially had to restrain the beam in the middle or like entirely, essentially, right, in order to stop it from compression buckling left and right. So if I don't have the objects on me to demonstrate, right? Imagine I had okay, you know what? We know what compression buckling looks like. The thing is, we have to restrain this compression flange, essentially, in order to stop the lateral torsional buckling. So if we had the equal angle, like you saw before in that detail, restraining the top flange, it's going to not want to move left and right. So instead of doing this, it'd be like, oh, and then like, I don't know, that's kind of dumb, but like, you know what I mean? And then as it goes down, it can't really go to the side. So that is called a lateral restraint. So that's as if there was an equal angle here. We would now consider it L, laterally restrained. So the thing is, if this was on the bottom flange, right? Say here. Do you think this would prevent lateral torsional buckling? Probably not, because it doesn't do anything. It just restrains the tension flange then. We're going to have the same issue with compression. So in that case, this would be nothing. This would not be considered laterally restrained. But we had that first case actually. So yeah. Point is, lateral restraints don't matter for alpha M, right? All that matters for alpha M is what's happening on the bending moment diagram between the full or partial restraints. For alpha S, it does matter. So the entire length here was 8 meters, right? The distance between restraints was 4 meters. And when I say alpha S, we're talking about slenderness reduction factor. We're talking about the length that we actually care about is between full and partial and lateral restraints. Okay, so that's gonna be 4 meters there, right? In my first pass of this video, I wrote down 2 meters. I have no idea where I got 2 meters from. I think that was just me tripping out because I was doing it like late at night. And I wasn't like that prepared, to be honest. So we have to multiply this by a couple of different factors. So there's your KT, KL, and KR factors, which I have in this table here. KT, we look at the restraint arrangement, and ours is FL, right? So for FL, we just have a restraint of 1, so we don't have to do anything else there. for KL, was it KL before? I meant KT before, but for KL, essentially, we're looking for the same restraint arrangement, but now we care about the longitudinal position of the load as well. So when you have a uniformly distributed load, that's considered to be positioned within the segment, right? Which kind of makes sense considering this is a segment, so all that's within the segment. If we had a point load, say there, then that's called at the segment end, which is that second row on the table, right? Yes, so next we care about the load height position. So there's shear center and there's top flange. It says in the question is top flange loaded, but that just means that a uniformly distributed load is positioned at the top flange. Shear center would be if there was something weighing it down from the middle, basically, instead. So that gives us 1.4, basically. So that's what we're going to go with. Cool. So we multiply everything. Oh, I didn't cover the last one, did I? Sorry, my bad. It also says in our question that there are no ends with lateral rotational restraints. And that is our default case. So if the question doesn't say that at all, just assume that, meaning that KR is 1. So as long as the question doesn't say otherwise, you should take KR as 1. Yeah, cool. Now we're ready to move on. So essentially we've multiplied our effective length by 1.4, which is significant, right? That's the top flange loading factor. Instead of 4 meters, we're considering 5.6 meters. That's a sizable increase, right? In terms of like the longer your effective length, the more susceptible your beam is to laterally torsionally buckle, right? So we have our standard material values, right? Elastic modulus is 200,000 MPa. Shear modulus is 80,000 MPa. That's standard. That's across the entire course. On one steel, what you want to nab here is IY, J, and IW. So that's your moment of inertia in the weak direction, the minor direction. J is your torsional constant, and IW is your warping constant. So grab all that from one steel. All you got to do is look at, split up. You go to the dimensions page, and you can look in this row, these columns on the right here for torsion and warping, and IY. So just be careful with IY is 10 to the 6. J is 10 to the 3. IW is 10 to the 9. So these are all going to kind of be a bit different. So just make sure you're writing everything down correctly. They also have different units for warping constant. But the units, yeah, you're not going to have to convert the units, it's fine. So now we just plug everything in, keeping in mind that this is 5,600, right, millimeters. And when you plug that in, you should get 207 times 10 to the 6. Now that's in Newton millimeters. So when you convert that to kilonewton meters, you have to divide it by 10 to the 6, giving you 207, right? So when we see MO, we go 207. MS was 360, which is what we calculated before we did the alpha values. And that gives us a value of alpha S is 0.429. Now, that is a significant shrink in capacity, right? But we did also get a fairly significant buff in capacity of 2.25 from the fact that we had a bending moment which looked like that, right? The thing is, we have to check quickly whether these two numbers multiplied together is greater than 1 or not. And when we do that, we get 0.966. So what that means is that your member capacity is going to reduce your section capacity by, so MB is 0.966 ms. It's going to shrink your ms by 3.4%, right? Is that right? That sounds wrong. 3.4%. Yes. Okay, anyway. So it's going to shrink it by a bit. If you get a value that's like 1.5, you essentially have to set it back down. So this would be back down to 1.0, right? Because you can't have that limit according to this formula. You can't go over that limit of ms according to this formula, right? That gives us 347.88 kilonewton meters. So that's down from 360, right? Okay. Now, this is our final capacity once we've shrunk it by 0.9. When we plug in what we found for ms as an expression of WQ, right, we get this value. So WQ is less than 24.49 kilonewtons per meter, right? Fantastic. So that's our value for flexion. Now we have to check shear. So for shear, sorry, I'm gonna have to re-upload my notes earlier. Let's go up and find it, but we did nab it from earlier. This one. So here's our shear. Yep, so that's our shear value. What we have to do is we have to work out the right hand side. So this is a minimum web thickness check. So we're checking whether this value here is allowable. So One Steel designs all its products. So we have a 410 UB, right? Something. One Steel designs all its products so that they pass this check. They pass this minimum web thickness check. But we're just gonna do it anyway. You can skip it. I don't think it'll reduce marks, but I'm just going to tell you how to do it anyway. So it's this formula for an unstiffened web bound by two flanges, right? One flange, two flange. We plug in D1, which is the clear depth, the depth of the air between the two flanges, right? Divide that by 180. You'll multiply it by the square root of our yield strength divided by 250. It says that our minimum web thickness, our thickness has to be greater than 2.3 mil. So when you look on One Steel, our thickness is 7.8 mil. Obviously they know what they're doing when they're designing these products, right? So that's completely fine. Now we go through a bunch of checks for shear. So the first check we have to do, let me show you on my shear notes, right? We have to go do a, look on the right hand side here, shear yield capacity check, followed by shear buckling capacity check. We have to find what the shear capacity for a uniform shear stress distribution is before finally finding our final shear capacity. So let's do that. The first one's our yield strength, shear yield strength. It has this formula where AW is made up of D1 times TW. So we found TW, so we went on One Steel, we found TW. We went on One Steel, we found D1, right? And we knew FY, you can look on One Steel, but we found that from even our flexion part, right? So 300 MPa, plug in the other numbers, here's what we get in terms of kilonewtons. So you're gonna get newtons first, you're gonna divide it by 1,000, you get kilonewtons, right? Next, we do a buckling check. So this depends on the web's slenderness, essentially. That's your beam. If your web is really slender, like I've drawn there, what can happen is that you're in shear, your web can buckle before it ends up yielding. Yielding is actually a pretty good scenario. Yielding would be if it was thicker and it ends up doing this. So you've essentially exhausted the max capacity that your web can handle because that middle web part was not super slender. So we're checking the buckling capacity now. So what would be its capacity if it were to buckle, right? So all we do is we chuck in this formula and we chuck in 381 for DP, which is the same as D1 in our case, right? It's only different if you have lateral shear stiffeners, right? Like here. So that's our, anyway. It's the same thing. If you don't see a horizontal line in between the flanges, DP is D1. yeah, chuck everything in the formula to find this value here. But same thing as MB and MS, right? We're saying VB has to be less than or equal to VW. So if you get a higher number like I did here, I got 1,256. You have to set it back down to the lower number, which is VW, right? Next is our uniform shear stress distribution. So we have to do a quick if statement check, right? So if we look at my notes, you're checking whether the web panel slenderness is low or it's high. So if it's low, then this statement will be true. If it's high, then this statement will be true and then it'll buckle. So if it's low, sorry, I should say, this statement will be true and then it'll just yield. So think about it. If you have a low slenderness, you're gonna experience yielding, right? So like compression. So this drink bottle, right, is gonna be quite compact. It's not gonna be very slender. If I were to crush it, it would do a yield failure. So maybe something a bit longer than this pen, but the ratio of like its cross-sectional depth to its length is like longer, right? So there's a chance that this could buckle, right? Realistically, well, something longer maybe, like a ruler or something. Same thing happens for our web panel essentially, right? So we just do this check. In our case, we found that the first case was true, so it was a compact web, right? So our web looked a bit more like this, which, you know, that's not gonna be more like this. That's not really gonna yield, right? If it was super slender, like that could, oh sorry, did I say it's not gonna yield? It's not gonna buckle. If it was super slender, it's gonna buckle. Okay. So our uniform shear stress distribution is governed by yield failure. The last step, VV is equal to VU, right? Basically, we say for our UB sections that it has a uniform shear stress distribution. So what do I mean by that? It means that tau is going to look something like this, right, for a UB. Basically, the web takes on the majority of the shear, right? That's that chunk there. What we're saying is that the average, sorry, the max, right, which you can find in the neutral axis, over the average is going to be less than 1.1. That's the definition. But we just assume it for a universal beam, basically, right? But yeah. So lastly, we plug in everything. So we plug in that value that we found for V star in that first step, and then we set it. And so the value that we get for our max distributed live load is 62.59. That's higher than what we got for flexure. So obviously WQ is going to be governed by flexure, because as you increase your load, your live load, it's going to fail in flexure first. It's going to do that lateral torsion or buckling thing before it's going to break in shear, in a yield shear kind of manner. Okay, that's it. Thank you. I did also give you a beam column question to look at as well if you'd like. And yeah, that's got gamma method, moment amp, combined checks. Have fun. All right, thank you guys.